So I'll be talking about modeling scheduler for in-order processors in LLVM. We'll see what's present, so what's easy to model and what's kind of missing or it's there but you have to spend more effort or make it more contrived. Right, so content-wise, a brief introduction to the LLVM machine scheduler. For those who are familiar, it will be a bit boring. Then we'll introduce something which I invented, to be honest, for this presentation, but it's very interesting. It's a collation of all the features, the key features you would have in an in-order processor. Yeah. The reason for that is because we'll then see how to develop the scheduler for that processor in an LLVM, and we'll use that as the backdrop, or if you wish, to discuss what are the things which are present and easy to model and what are things that are missing. So that makes it much easier than talking about one specific processor and its limitations, etc. Right, so let's get going. Right, just a reminder, okay, most of you probably already know it much better than me. What's instruction scheduling? Instruction scheduling, you are basically reordering instructions to improve performance. More specifically, you're trying to reduce the pipeline stalls and increase the number of issues. So if you got like dual issue, you want to every cycle issue 2 instructions. Bit of terminology, there are 2 kinds of processors out there and things in between. So you got in-order processors. In-order processors are where the program, the processor fetches the instruction in the sequence that it sees in the assembly, executes them, and commits the results. Right. So it just follows the schedule that was given by the compiler, if you wish. Out of order, the fetch is still in the same order, the program order. The commit of the results is in program order to make sure things are working semantically correct. But in between, the processor has the flexibility to set instructions going for which the data and the resources are available. So for example, if you got 2 adders and a multiplier and and the multiplier is busy and there's another multiplication in the pipe waiting, you say, okay, I haven't got resources, but I've got ALU, I'm going to start the ALU on. Right, so that's in order, out of order, and the focus in this presentation is for the in order. One of the reasons is for in-order processors, the processor is much more relying on the compiler to do a very good job. Right. In general, of course, again, this is just a small quick reminder to set the context. Scheduling algorithms typically work like this. So you got instructions and you got dependency between instructions. So you create a graph and you could annotate the edges with the latency, so how long it takes to compute the results. And then any topological sort of this is a valid schedule in a way. But there are many options, so it's an NP-complete problem, as you know. So which one is the right one is hard to know. It's an NP-complete problem. So we resort to heuristics, and that's the heuristics that's used mostly. So that's what list scheduling is. And typical heuristics are like critical path, register pressure, and other things. Right. To do a good scheduling, the compiler needs a lot of information. It needs to know what the processor pipeline looks like so it can do a valid and a decent schedule. So you need to know latencies, resource cycle, micro-ops, a bit. So resource cycles is like, it needs to occupy the resource for how long. Is it fully pipelined? It's not pipelined, things like that. Talking specifically of LLVM scheduler, the one that we will focus on here today will be the MI machine scheduler. So it works at the machine instruction level. It's the latest and greatest. It's kind of the scheduler of the future. You encourage more to use this one. It's very effective. At its heart, it's a scheduler with prioritization. It uses priorities and heuristics. And it's a per operand. So we'll talk a bit more about it later. So very high level wide is like, suppose you have an addition and you need 2 inputs and an output. When do you need the inputs? When do you produce the output? Right? You can specify exactly that. So for some other instructions, for example, you may not need all the inputs at the same time. And you may not produce, if you're producing 2 outputs, you may not produce them at the same time. So those nuances. Enabling the scheduler is rather straightforward. You just pass some enabling options, and you can also choose some flags for top-down, bottom-up, which way you want it to proceed. But of course, it's behind it, you have to have the information to enable it to make the decision to do the schedule. It's not enough to just switch it on. Well, you switch it on, but there's nothing behind it, so it can't do much. Right, so now we'll talk about the generic in-order processor and to see what key features there which we want to model. Right, so in any processor you would have function units. So in this case I just picked, like, say 2 ALUs, 2 multiplier, 1 division. They may be fully pipelined, or some of them may not be fully pipelined. You have instruction fetch, so a unit which fetches instruction, 1 or more instructions, and then decodes and issues the instruction. And there is a scoreboard mechanism which keeps track of which instructions are ready for being launched into the pipeline. For example, are the data ready? Is the resource available? So that's the scoreboard keeps track of everything. And you have branch prediction, because otherwise, if there's a branching and your pipeline needs to be filled up, so you need to know whether the branch is taken or not taken. Right. So just a picture is what 1,000 words. So take you through. So you got on the left-hand side the prefetch unit. So you can have multi-stages. So this is where your instructions are fed in, the address generation unit. And so, like, for a branch predictor, the job is to tell it where, for a branch, where the target is going to be, whether it's going to be taken or not taken. The instructions are fetched in advance and put in an instruction queue. So that's where it's all there most of the time. For ready for pickup, so you can pick 2 or 1, depending on, again, your specific processor, how it works. In this case, in the diagram, you see 2 instructions are fetched and decoded, and then they are issued, and then they flow through the pipeline. As I was saying before, okay, in this case, we have 2 ALUs, 2 multiplier, and you got scoreboard logic and forwarding bypass logic. A bit more, some more was on the forwarding logic. Right. So suppose you have this sequence of instructions. So you got shift, and the output of shift, R0, has to be read, is an input to add, and add produces R2, and that's an input for the store. Now, in a very old processors, what you would do is, after you write to R0, only then you can read the input, and then add. So everybody waits, but that's a lot of stalls and wait. So in the modern processor, what happens is, as long as you know, let's say when add reaches the stage of the pipeline when it needs to really read it, it can't let it read it, the value, it does it any later, and if you're fine with it, then you issue it. So in this case, for example, just let's say add, it needs the input at stage 2, and in this case, the shift happens in stage 1. So you know that by the time the add reaches stage 2, the input to it will be ready. Similarly, for the store, again, you see it needs it in a much later stage. The value that has to be stored, it needs it in stage 3, and if it's going to be ready, you issue it. Now, all the time it doesn't work so nice, hunky-dory. So sometimes you'll have a stall. So when you need to, it's just like you're loading something from memory, and there's no way you'll have the data ready, right? So one more feature I need to introduce before we have a full picture is the dual issue. So you got your program sequence, and instead of picking 1 instruction at a time and issuing it, it picks, let's say, 2 instructions or 4 instructions and wants to issue them together. Now, for data reasons, so data dependency reasons, it says, okay, so the first instruction is the one that has to issue first, let's say, and it says, yes, I can issue it. Can I issue the next subsequent instruction also at the same time? Well, the first thing is to see whether these 2 instructions are dependent on each other. Well, if they are dependent and you can do some forwarding, that's also great. You can dual issue. Or if you don't have enough resources, so for example, you got 2 load instructions and you just got a 1 load store unit, you can't dual issue, right? If not, then you move down and try the next 2 instructions. So that's how one mechanism by which this dual issue would work, right? And of course, it's not all possible all the time to be able to dual issue because you have constraints and all kinds of constraints. Resource, data dependence, some instructions, like let's say you are loading the PC. So suppose you want to change the program sequence, right? So just a picture again on how it really flows through the pipeline in the hardware. So the way to look at it, in this particular example, you've got two issues. So a multiply and a subtract are issued at the same time. They go through the pipeline. So the multiply goes through stage 0, 1, 2, 3, and same with the subtract. Now it turns out that this ROR, the rotate instruction, needs input from the multiplier, but the multiplication product is generated only in the stage 4, so you have a stall. So basically you have two cycles in which the pipeline is stalling, is waiting, you don't have good efficiency. And because you have issued them together, the add as well, so the ROR and add were issued together, these two stall. Now this depends, I mean, different implementations would have different way the processor behaves, depending on how many gates you want to dedicate to this kind of logic. Well, this is just one way that things could work. Right, so that's how a typical, let's say, in-order processor you got. Forwarding, you got dual issue, or quad issues, or single issue, and different resources. Let's see how now in LLVM you can model it. Okay, right, so before the big picture. So when I started working on it, you want the lay of the land, like, you want to find your way to some, so you start looking at classes and trying to put a picture together. So this is an old picture I drew for myself, and I said, okay, maybe it's a good way to share how complex sometimes things can get, and once you see it, it's pretty straightforward, right? So the way it's done is pretty nice. So your machine scheduler is a pass. So it's a pass that goes through your functions, your basic block, and creates something called region. Each region ends with, say, a function call or a branch. So you got a nice piece of sequential code that wants to schedule. The scheduler is, schedule diag MI is an implementation of stag instructions. So basically, this is your bookkeeping part, the scheduler itself, which initiates the queue, keeps track of instructions, etc. But your actual scheduling policy, what kind of scheduling you want to do, that's determined by this class. This is the sketch strategy. Therein, let's say you don't like this scheduler, you want to have your own fancy scheduler. That's the part you need to rewrite. So you can pick and choose what part you want to override with this modular approach, right? Okay, so let's say you take the vanilla, whatever is there, two key functions. So there's one called the pick node. So as you get scheduling, every time you have to make a decision which instruction I should schedule next. And then every time you try with different other options that are available. So you look at the ready queue, what else could I schedule, right? Now, in the scheduling, you would say, okay, this instruction I look at and add, I need to know a lot more, what resources it needs, what latencies, etc. So that's where if you see here, the stead model comes in. So by the way, we named our in-order processor cart, so we say cart model. And a lot of you would have heard about Tablegen in LLVM. That's where Tablegen comes in. You give your entire description of your pipeline in Tablegen language. So it's also modular. It's not like one big mammoth. So it's hierarchical. So at top level, what you describe is, okay, I've got an in-order processor, two issues, and then some other things like low latencies, etc. So you describe at a high level that. Now, what happens to this Tablegen, just for curiosity, right? If you're wondering. So this is a domain-specific language. What LLVM does is takes that description and calls the Tablegen and generates a lot of records, so structs. And that is incorporated in your MC target descriptor. So in your LLVM target, when you're sub-target, when you're going through it, you can at any time say, okay, for this instruction, I want to know the latency, what resources it needs, and all the associated information. That's how it gets the information. Right. So when you get down to designing the model in LLVM, in Tablegen, you want to describe your pipeline. There are the way I see the two broad ways you can do it. The first one is nice and easy. It's a target-specific approach. So what you do is modify each instruction that you have for your target to inherit from a type called sched. and associate each operand with sched read write type. And in the sub-target, okay, so there's a lot of words, but I've got examples. The second approach is you define things for your sub-target specifically. So let's say you got a sub-target which doesn't fall in the template of your, let's say, your target, right? So in that case, you want to really specify things yourself. So an LLVM Tablegen gives you that flexibility to do both ways. And for this example, we'll do both. So the first one, pretty straightforward, just one slide, I think. Yeah. So is the following. So this is again Tablegen, but this is describing your instructions in LLVM. So at the top line, you say, okay, def write ALU. So you say, okay, I have a type which writes to ALU. You don't say much more what it does. And then in the here you see the instructions. So you have defined in LLVM an ALU instruction. So you have an ALU instruction and all those gibberish there. It means it's trying to say it. Okay, what inputs are required, how you can do a template matching when you're doing generating instructions. In addition to all those things, so and this part, if you can see, this is the one that generates the assembly, for example. It inherits from the sched write ALU. So you modify your instruction to inherit from the sched read write type. So you say, all you're saying at a very high level is that this instruction, this ALU instruction, does a write to ALU. Yeah, of course it does. What else would a write ALU? What else would an ALU instruction do, right? So you say, okay, so you get down to the sub-target. So, and here you add more meat to what write ALU means. So write ALU uses the ALU processor unit. So upfront you have defined, like for my processors, I have so many ALUs and multipliers. So you kind of link them up. And then you say, for the write, how much latency, how many cycles later this write happens. Then once you have put these things together, so you have, okay, for every instruction, what inputs are needed, what output is generated, what resources, how long it takes, and you glue it together. And that's pretty much you need for your sub-target, if you have done it in this way. If not, then you have a sub-target approach. So all you have to do here is some extra work to specify your own read-write, in this case called sched read-write resource. So first you define some types, and then again with the type you associate the ALU, the processor unit, and the latencies. So for example, let's pick like load. So you define a type that specifies a load. So for the load, you need a load store unit. So that's your load store unit. And you take, let's say in this case, 4 cycles to do a load. So that's what it's telling it. You have more like that. And there's something called read, sched, read, and read advance. It's another types in LLVM, which gives you the way to specify the forwarding. Very simply put, it's like when you see a 0 here, it means there is no forwarding. It needs, that instruction needs the input right at the beginning. So for example, you're doing a load, you really want the address to the load, otherwise you cannot do anything, right? Let's say a store, well, you don't need the value that you're going to store maybe right at the beginning, so you can wait. So these things tell you how many cycles later you need the inputs. So once you have set up those definitions, what you do then is connect them together. So let's say from the top one, what you have is, by the way, these are in like regular expressions. So you have like add. So the first one is showing an add register immediate. So it needs a register value and produces one output, and it says an immediate. So it says, okay, when I'm adding a value and in a register and an immediate value, then I have something called read DP2. So it's named, in this case, okay, I read it in stage 2 of my pipeline. And I produce the output in the stage 3 of the pipeline. So this is just naming that you do if you're writing proper code so that anybody reads it, understands what's happening with your pipeline, right? It's the right way is to associate the right numbers you saw in the previous slide. So like see here, DP3 is 2. Okay, why is 2 not 3? Depending on what your baseline is. You start at 0 or 1, right? So putting it together, okay, how do you describe a model for your pipeline in LLVM? You go through a series of definitions and you connect them together. And that's up to now what's been presented. Well, I left out a lot of nitty-gritties or details about certain kind of things. For example, what happens when you have multiple outputs? What happens when you need to occupy resources for a long time, right? So that's additional things. Now, with that background, now what's present? So what's present is very easy. So what you've seen, we have done so far, right? It's easy to describe. It's a hierarchical model. It's compact if you're inheriting from SCADs, etc. I guess you're more interested in what's missing, because that's something, if you're a PhD student, you want to work on straight away, right? So instructions with slot constraints. So that's the one that I was talking about initially with the dual issue. Suppose you got 2 instructions, and there is constraints between them that you want to describe. Now, in the current framework, how do you do it? And is it easy? So let's go one by one. So if you cannot issue in second slot, so you got an instruction that it can be in the first slot but not in the second slot. Well, you need some way to annotate it. And the way to then take care of it is to write your own scheduler, make some small changes so it knows when the pick node knows what to do. Cannot issue with any other instructions. So you got an instruction that just wants to go down the pipeline alone by itself, right? Well, you can, again, there are other things like micro-ops you can use to fill up your pipeline. So when it's issued, nothing else can be issued. Cannot issue with another instructions. So there's some more like that. Right. So another interesting thing is, like in real pipeline, sometimes you happen that you see it as at one level as one stage, but it can take inputs in the beginning or in the end of that. So internally, probably it has more clocks running. So you see it as one clock cycle, but internally to the hardware guys, it's not one clock cycle. So how do you then model that? Well, one way is you just, okay, I don't care about the high level clocks. Tell me how many clocks internally, and I'm going to describe my pipeline like that. But then you might end up with now 20-stage pipeline, and you've got a huge SCAD read writes and stuff. So then you have to trade off, okay, how much benefit you get out of it. So the last point here is not really that's something that's missing, but it's something that when I did my descriptions, I found it tends to get very large. So when you have instructions that generate multiple outputs, the way to correctly describe in LLVM, it takes a lot of code sequence, and there should be a way to represent it more compactly. I mean, if you have to write long sequence of code for just one cases, then it gets pretty big, right? So in conclusion, you can get significant performance if you write a very good model for your pipeline. Most pipelines are rather easy to capture. Now, there's some parts of the pipeline which are dynamic decisions made by the processor. So there's no way you would be able to really model it, because you don't know how the pipeline is going, the processor is going to behave. Because, for example, let's say how the cache is going to behave, and things are going to change. You may think you have got it all tied down, but the cache behavior is hard to model. Some aspects in the pipeline, the LLVM are harder in the current Tablegen description to describe in terms of length of description, etc. So that there is again room for improvement. Yep. So with that,